Modern enterprise networks are sprawling, decentralized, and complex. Data constantly moves between endpoints, servers, and cloud environments, rather than staying within a single, isolated mainframe. Opening internal corporate databases to external nodes introduces vulnerability. Every remote connection is a potential vector for malicious traffic to enter the core infrastructure. This reality establishes a bedrock axiom of enterprise networking. A secure, intelligent perimeter is required to inspect and control what enters and exits the system. To enforce that perimeter, network engineers deploy specialized hardware, specifically the Cisco Adaptive Security Appliance, or ASA. The ASA performs a vital dual function. It centralizes the management of network security rules and enables secure remote access through virtual private networks. Welcome to Lecture 10, Advanced Adaptive Security Appliance. I am Dr. Ala Jabar Al-Maliki, representing the School of Computing at University Utara, Malaysia. Programmable gateways allow the ASA to enforce specific security logic across every packet entering the enterprise environment. Historically, configuring complex security hardware required engineers to memorize and deploy hundreds of raw text strings through a command line interface. To reduce this management friction, Cisco developed the ASA Security Device Manager, commonly known as ASDM. ASDM is a graphical user interface engineered specifically to configure, monitor, and manage Cisco ASA devices without requiring deep CLI expertise. It provides engineers with a visual dashboard for real-time monitoring of network health and offers a simplified method for configuring complex firewall rules. Setting up secure cryptographic tunnels is a demanding process. ASDM utilizes a built-in VPN setup wizard to streamline these deployments. It also includes capabilities for advanced logging and traffic analysis, giving the network engineer immediate visual feedback on the data flowing through the appliance. By abstracting dense CLI strings into actionable visual telemetry, ASDM allows engineers to parse network health and deploy security policies significantly faster. Choosing between ASDM and the CLI is an engineering trade-off based on the specific requirements of the task at hand. This matrix compares ASDM and CLI. For ease of use, ASDM is better for beginners. For flexibility and speed, the CLI dominates, allowing faster, customized scripting. But under visualization, ASDM uniquely renders traffic flows into visual charts. In a practical scenario, if an administrator suspects a network breach, ASDM allows them to rapidly monitor anomalous traffic flows visually, spotting spikes in data usage instantly. It also allows an administrator to visually manage active VPN connections, seeing exactly who is logged in without parsing through hundreds of lines of raw text logs. A complete network administrator must be proficient with both interfaces, leveraging ASDM for real-time visual analysis, while relying on the CLI for rapid, granular configuration changes. The second core function of the ASA is establishing secure remote access for individual users connecting from external locations. A remote access VPN is a mechanism that simulates a local network presence over an untrusted public connection, such as a home network or a public Wi-Fi hotspot. This split-screen diagram shows two ASA protocols, IPsec and SSL. IPsec utilizes heavy encryption and strictly requires dedicated VPN client software installed on the end user's machine. An SSL VPN operates through a standard web browser, creating a lightweight encrypted tunnel directly to the ASA. Because SSL relies on software the user already has, it minimizes IT overhead. Administrators do not have to update and manage third-party client software across hundreds of remote laptops. The choice between IPsec and SSL dictates the deployment burden. IPsec demands rigorous client management for maximum control, while SSL prioritizes agility and frictionless access for the user. Constructing a VPN on the ASA requires a strict 5-step logical pipeline that translates security requirements into executable code. This pipeline has 5 steps. Step 1, define address pool, reserves internal IPs. Step 2, configure authentication, verifies credentials. Step 3, configure group policy, sets network permissions. Step 4, configure tunnel group, binds parameters. Step 5, apply security policies, enforces traffic filtering rules. These steps are sequentially dependent. If you fail to configure a proper address pool or set up authentication correctly, the entire pipeline halts and the connection drops. A secure VPN configuration is a sequence of highly dependent logic gates. It methodically converts an untrusted external signal into a verified, highly restricted internal session. Let's apply this pipeline to a practical deployment scenario. A University Utara Malaysia employee attempting to access internal corporate servers securely from their home network. This animation traces the connection path. The employee initiates the session, and an encrypted SSL packet travels from the remote laptop until it arrives at the physical perimeter of the Cisco ASA. The ASA intercepts the packet and executes step 2 of the pipeline. It holds the data and pings the university's external radius server to verify the user's credentials. Upon approval, the packet is cleared to proceed. Next, the ASA establishes the tunnel by executing steps 1 and 4, pulling from the address pool to assign the packet a valid internal IP tag. This allows the packet to move through the physical boundary of the firewall. In the final access phase, the ASA enforces step 3, the group policy. This dictates exactly which internal servers the employee can communicate with and which critical systems remain invisible to them. By applying this step-by-step logic, the ASA successfully engineers a completely secure, isolated pathway through the public internet. Configuring a VPN is not sufficient on its own. The architecture must be actively defended through strict operational best practices. Here are the primary defensive measures required. First is enforcing strong encryption standards across all tunnels, specifically the Advanced Encryption Standard, or AES. Second is the necessity of multi-factor authentication. MFA prevents compromised or stolen passwords from being used to bypass the ASA's perimeter defenses. Third is the operational requirement to continuously monitor active VPN sessions using ASDM, ensuring that access is restricted based purely on the specific roles assigned to the users. I am Dr. Ala Jabbar Al-Maleki. Thank you to the School of Computing students for your attention to Lecture 10. True enterprise security is a continuous cycle of rigorous architectural design, real-time visual management, and strict adherence to cryptographic best practices.